Right, I'm going to start with, they go through separate sections again. They break this down a bit further than I think is good nature for you to learn. They do a section on equations 1 and 2, and then a section on equations 3 and 4. Then they treat gravity as separate. I'm going to do a couple of linear ones, and then I'll do a gravity question with you as well. And we'll see where we are from that point moving forward. So, the question I've got first of all. I want to know how long, and this is a gravity question, but it's reasonably straightforward. There we go. We'll be writing some of these down again as we go through. So, under gravity, a coin falls.
Is this section 2.6?
This is, I'm doing an example from 2.6 just because it's one of the easiest ways to get the idea of constant acceleration. You're used to it dropping. It's not an example from your book. Okay. This is a different example just to show that the gravity questions, they're not really any different to an constant acceleration horizontally. But I'll do a more complicated horizontal one in a minute. So under gravity, a coin falls from rest. There's one of your keywords. From rest from 12 meters. And the question is, how long does it take? Now this is fairly grotty numbers. It's because I took it from an MEI book, not from an Excel book. So what information do I know? Often worth drawing a diagram to start with. So a coin, we're going to consider the coin to be a particle. What does that mean for us? First, it's got no size. So with that no size, it actually, what's that mean about air friction? No air friction. Yeah. The particle also means, because it's got no size, we've got no rolling motions. It just moves magically. We don't know if it's sliding, we don't know if it's rolling. It's just moving magically, so there's nothing to worry about with them. That's the point about a particle. What does rest mean?
0 7.
Yeah, so we now know a variable u equals 0. 12 meters,
Starting height
that's my s. And what does gravity tell you?
9.1 meters.
Yeah. If you read the front of your exam paper, always do this when you go into an M1 paper. Look at the quantity that they put on the front. Most of the time, they say G is 9.8 per second squared. I have seen, not in an M1 paper, but I have seen in later papers, where because of people using 9.81, they've lost marks for being an unsuitable level of accuracy because of the nature of the type of question. It was saying that we are limiting these values to certain limits. So just be careful what value you're using. Partly because if you use the wrong value, half the time the cancellations don't work. If you use 9.81, a number you'll often see in a lot of questions is 19.6. And that's because it's 9.8 doubled. Right, so if you overcomplicated your number, you can cause yourself small problems. So let's draw a picture. So the first thing is I've got my particle at the start. I'm going to say this is at time equals 0. And it begins falling to hit the ground after 12 metres. I'm an engineer, so to say ground, we normally put cross-hatching. What happens is the distance. We know the distance there is 12 metres. And we know at the top here, our U is 0. Now, by convention, different arrows have slightly different meanings. If you put arrows on both ends, you're normally talking about a distance. If you put a single arrow, and I put a single arrow head, you're talking about a speed. And if you put two arrows, that's showing we're changing the speed, which is my acceleration. And acceleration is 9.8 meters per second.
Oh, so G is A in this case?
Yeah, G is what leads to our acceleration. Sorry, I should have said G first.
Second square? Second.
Yeah, squared.
Minus.
Yeah, and that should be an A. That's my acceleration. What is it we're trying to work out?
Time.
Time. So this is where I said, let's do our SUVAT. We've got our diagram, we know what's happening. One tip for you. Once you've drawn the diagram, decide what direction is your positive direction. It's one of my big tips. Logically on this one, what's the logical direction to say is positive?
Down.
Down, yeah. So I would always put a little diagram on my arrow, going like that, and say X positive. It helps remind you exactly what's happening with that diagram. I'd say it's good practice to do it, so you spot mistakes a bit quicker.
Okay.
Yeah. And that sort of means that my displacement now sort of has a time going from top to bottom. So in the book, they may put two arrows. I tend to put two markers. And now I know where the start is. I will definitely put an arrow to a point. So that's an alteration I tend to do in my diagrams. It's my way of showing displacement, not distance. At the earliest time, where am I measuring from the earliest time? Where am I measuring to at the end? And it just helps me orientate where my X's are. So let's write out SUVAT. S-U-V-A-T. And we go through and we put in what we know. S. Now I'm going to put signs in as well, so we're thinking about this direction. I want a positive 12 meters in the direction of positive X. U, I know was 0. Doesn't actually matter. I'm putting units on just to get used to doing it. You don't always put the units in when you're doing SUVAT because you're really just collecting the information together. But I'm trying to emphasize the units you should expect, and thank you for correcting my gravity. V, do we know V?
No.
Leave it blank. A, do we know A? 9.8 meters per second squared. Is it positive or negative in our diagram? Positive. And time, do we know it?
No.
Do we want to know it?
Yeah.
Yeah, so we now need to think which of our equations links S, U, A, and T. And you can go back up to the top. Think it.
The last one.
Does the last one contain T?
No, sorry, third.
Third one, S equals UT, add on a half AT squared.
Wait, could we, for example, use the last one and then do another one to find T?
You can, but you're doing extra work.
Yeah.
Yeah, but you can work out the other missing value. I was going to ask about that one. I was going to say, we might actually do it and see what can we say about this, what this means potentially, because it does actually have a meaning, what can happen with that one. So we now put in, we think, S equals UT, add on 1/2 AT squared. You don't get marks just for writing the equation down. So the first version,
Or we do?
you don't.
Oh,
But you will get marks for showing correct substitution normally, your first method mark. So S is 12, U is 0.
Right in the booklet, right?
No, there's no mechanics formula. You need to learn them all. Luckily, there's not actually that many, and most of them make a bit of sense. So U times T. We don't know what it is, so I'm using T. Plus 1/2 9.8 T squared. And so now I can rearrange this or solve it. So I've got 24 over 9.8 gives me T squared. And therefore T equals, and now it's a case of find your calculator. 24 divided by 9.8. And this is one thing I would show as well along the way. I would put in, each time I get an answer, I'll put in at least 4 significant figures on them. Because the answers in mechanics are normally expected to 3 significant figures, so work at least at 4. Ideally, use the memory in your calculator. And then do the square root of that answer, which should be about 1.6, yeah, 1.56.
and we're working with the positive value, right?
Well, I was going to ask you, we get a positive or negative value.
Positive, always positive.
We're going to choose the positive. Now, the point about the maths is the maths doesn't actually know about the physical situation. All it knows is we've told it about a point at the top here and it falls. Well, that shape is actually a parabola. You take a ball and you drop it. As you get faster, you should actually recognise it as a parabola, especially if I try doing it. Sorry, Richard, you won't see this bit. As you watch it bounce across the room, you should recognise a series of parabolas. So what's the negative one telling you?
That it's going up.
Yeah, it's the other half. It's before that, there was another time you could mathematically find a negative time. Before that, assuming it went up to here, we've just worried about that side. It's also telling me about an answer if I threw it from over here. And that's part of what the second part I was going to deal with is.
So if you need to calculate the balance, that would be, it would have to double that?
Essentially, what we're going to say is we shouldn't be quoting answers before the very start of the question. The start of this question was it's starting from rest at the top. We haven't been told how it got there, so we can't say it got thrown up so that we have a time when it before here. So before the question, assume there's nothing going on before the question starts because we know nothing about what happened. Let's have a look at the, Tal said, oh, could I start with the velocity one? Well, you can, it will go a long way round, but we'll try it. And this will tell us the final speed. So the first one, let's go, and in this case, you could actually do it as V equals U plus a half AT squared. But there's a reason I'm going to use the other equation. So I wanted to do that in greenish. So V squared equals U squared plus 2AS. We'll use the numbers from the equation before. So put in purple. I V squared is 0 squared plus 2 times G times 12. So V squared, or V, is the square root of
It's 14 root 30 over 5.
8. It's going to be something like that because the way they sometimes do it. So we start off with 235.2. 100, yeah. And then square root it. No, that is give me a cube root. Square root 235. 5.2. And that gives me 15.3 meters per second. And in both of these, notice 3 significant figures. And this has a plus or minus, because it's a square root again.
Are we
Well,
allowed to write it as a fraction?
yeah, you can write it. Anything, it normally says all equivalent. Anything that will give you equivalent to that decimal number. And the marking normally says anything that rounds to 3 significant figures. Some of you might have seen in P3 paper, I think it was, the thing about the particles. Was it a number of items, or was it you had an n log equation, and you solved it and you got 2575 point something. If you gave me that answer, I was told to accept it, even though the question had said 2 significant figures. Yeah, but you gave a more accurate answer, and in that case, they're not too worried about losing that, not using that accuracy. M1, sometimes if they're being really horrible and looking for a mark in the question, they might do it once in a paper and say, you didn't give it to a suitable accuracy. Putting all the digits down, you've got to remember we're modelling, and modelling is about making certain assumptions. We've assumed there's no air resistance. We've assumed that the particle's not spinning, causing different vortices. All those assumptions mean that you can't be arbitrarily accurate. At some point, we're going to be wrong from the real world. So that's why their argument on modelling is you should be a suitable level of accuracy, generally 3 significant figures. What's the negative answer of that one telling you then?
Should be going up.
Think about where our direction is. Well, you said X was.
Yeah, it would be going up.
Yeah, that's the other one. The negative answer is when I throw it from before. Yeah, so that's what those 2 answers mean. Yeah, normally people model this with they like the X going up, and we get lots of minuses around, which is where those questions come in. All okay with the idea? Oh, actually, no, I can leave it. Let's do that like that. Okay with those? Do you need more examples, or are you happy with trying the ones in the book?
Is this the 2.6? Or
This we've covered 2.4, 2.5, 2.6. They break down the extra questions.
The second chapter.
No, not quite. We've still got quite a bit to do on other stuff, I think, in your book. We've looked in gravity. Sure, there was a bit more to do.
No, there is not.
There's not. Are you happy with those questions? I'll do one without speaking if you want. Richard, it's 1 o'clock. Or has he already gone?
Thank you, Mr. Woodward.
Thanks.
I'll go watch the videos. Bye-bye.
Okay.